Okay, so what happens if your object is inside the focal point? The rays you draw are the same, but you get a very different result. So I've just sort of made up some data here. The object distance is 5 centimeters and the focal length is 10 centimeters. So let's draw our two rays. Now the first ray, just like we did before, we'll draw principal to the parallel axis and it will reflect through the focal point. Now this is not doing very well, so let's just do parallel there. And then we'll go through the focal point out in this direction. All right, that's our ray number 1. Ray number 2 goes through the focal point and reflects parallel to the principal axis. However, I can't go from my object to the focal point because the direction is wrong. But the rays don't care who's what. The rays travel the same way. So instead of going from the object to the focal point, we start at the focal point and go through the object, just like this. And we reflect parallel to the principal axis, just like before. So ray 2 looks a little bit differently, but it works exactly the same. It goes through the object, it goes through the focal point. The reflected ray is parallel to the principal axis. So as we see, and as I've written over here and forgot to erase, the reflected rays don't intersect, okay? So if the reflected rays don't intersect, that means there's no real image, right? Because that's what it means. If the reflected rays intersect, we get a real image. That's when we can project on a screen, like a projector screen or a movie theater screen, okay? So if there's no real image, and this will happen anytime the object is inside the focal point. If there's no real image, we need to look for a virtual image, okay? A virtual image, one that your eyes sort of construct. And we do that by, all right, I'm going to write it right here. Locate virtual image. If you don't have this in your notes, it should be. Locate your virtual image by extending the reflected rays. All right, again, if that's not in your notes, it should be. Now I usually indicate that on my ray diagram with a dotted line. So here, I'm looking at reflected ray number 1, and I'm going to extend it like this, right? Here's my reflected ray number 1 over on this side, okay? I'm going to extend it out there. Now, what about ray number 2? Ray number 2 comes this way and reflects this way. So I'm going to extend, that looks messy, that reflected ray over on this side. Now, spoiler alert, they're going to converge on the other side of the mirror, okay? So here's my intersection, and what is that? That's my image, right? So my image here is right like this. So I didn't say this on the other video, but let's start to concentrate on what these images look like, okay? It's upright, okay? It's not upside down. Your real images are always going to be upside down, but your virtual images are going to be upright. Okay, it is virtual because it's not real. That's one or the other. Also, for a concave mirror, if your object is inside the focal point, this image is always going to be larger. Okay, it's always going to be larger, which means that your magnification is going to be greater than 1. It's also going to be positive, right? So it's kind of a weird way to say that, but I will recap the magnifications later. Okay, so let's do the math there. If my object distance was 5 centimeters and my focal point is 10 centimeters, where is my image? Let's figure this out. So using the LensCrafters equation, I'm not sure if yours has DI or DO first, but as you know, it doesn't matter. 1 over F minus 1 over DO equals 1 over DI. So again, I usually shortcut this. 1 over 10 minus 1 over 5 equals, and then I flip that, and I get negative 10 centimeters. Now, negative signs are important, critical in optics, okay? What does that negative mean? That means it's on this side of the mirror, all right? That's my negative DI, okay? Then the other thing you want to find is the magnification, all right? And you can do the magnification a couple of ways. You can do the height of the image divided by the height of the object, or you can do the image distance divided by the object distance, which we don't have this, so let's do this. The image distance is negative 10 centimeters. and the object distance is 5 centimeters, which gives you a magnification of -2. And it occurs to me that we need a negative sign in the formula, right? You're probably yelling that. I haven't taught this in a while, but yeah, we need a negative sign in the formula. So it's not -2, it's +2. The centimeters cancel out and the magnification is just a scale factor. So there's no units there. So that's our magnification for an object in a concave mirror that's inside the focal point. We get a virtual image, it's upright, it's larger than the object, and then we found the magnification. So that's a concave mirror with the object inside the focal point.